Welcome back. And last time we talked about using the periodic table to figure out D and S block, D and F block electron configurations, and then we talked about orbital notation, right? And how to use orbital notation to represent each electron in an atom, and then we used something called the noble gas method, which was kind of a shortcut. Now we want to build off this noble gas idea and come up with something called the outer level, oops, can't see that very well, outer level electron configurations. Yes, so what are outer level electron configurations? Well, they're the location. So let's define these first. Outer level electron configurations. Electron configurations. And what are they? This is the configuration, I guess the best way to say it. This is the configuration for the electrons farthest from the nucleus. Now, the way I think about this is these are electrons beyond the noble gas core. Okay, so we have a core group of electrons, right? And those are represented by that noble gas. And then we have electrons beyond that, and those electrons are defined as the outer level electron. And then we can have that configuration. So let us start with our sulfur, okay? So the first thing, the process for working this is pretty simple. The process for determining this is write the noble gas core electron core method. Use the noble gas core method. And then what do? Then subtract the noble gas. And what's left is my outer electron configuration. So we want to do sulfur. All right, let's go to our periodic table. Do I have a close? There's a periodic table. Where is sulfur? Here is sulfur. We want to do the noble gas core, so I am at electron 16. What is the noble gas prior to number 16? Well, it's number 10. So I'm going to start off with neon. And then what? After neon, I have to come all the way over here to what? 3s2. That's a nice 2. And then where do I go? 3p, 1, 2, 3, 4. Okay, good. So neon 3s2, 3p4. Let's go back and write that down. For sulfur, I have neon 3s2, 3p4. So this is my electron configuration, and I'm using the noble gas method. So how do I get my outer electron configuration? Well, I want to just, for the outer electron configuration, what am I going to do? Get rid of the neon. And what's left? 3s2, 3p4. That's my outer electron configuration for sulfur. That means these are the electrons that are farthest from the nucleus. It's that simple. Good. Let's do another one. Sodium. Okay, sodium, piece of cake. Are you ready? Sodium. Yep. Sodium is right here. Right? Sodium is 11. And here is neon. So it's going to be what? My total configuration for sodium is going to be neon 3s1. Okay, so neon 3s1. So for sodium, I have neon 3s1. So what's my outer electron configuration? I get rid of the neon, and so it would be just 3s1. Oops, not 31s, 3s1 for sodium. And the last one, vanadium. Okay, let's look at vanadium. Where is vanadium? Vanadium is right here. What's the previous noble gas? Argon. So I'm going to have to go with argon. And then what? After argon, I have to go through these guys. 4s2, and then these guys, 3d, 1, 2, 3. 4s2, 3d3. I get rid of the argon, so what's my outer electron configuration? 4s2, 3d3. Okay, so for argon, my answer would be 4s2, 3d3. That is my outer electron configuration. Good. All right. So I want you to do this for calcium, zinc, and tellurium. Pause me, and when you're done, I will come back and give you the answers. Okay, here we go with calcium. So if I look at my periodic table, I see calcium. Right before calcium, I see argon. Argon, good. Argon, 4s2. I get rid of my argon, so my outer electron configuration from calcium is 4s2. Zinc. I look at zinc. Hey, I see zinc is in my fourth period. That means I start with argon. And I go 4s2, 3d10. And I get rid of my argon. And so 4s2, 3d10 are my outer electrons. And then tellurium. Tellurium, I see tellurium is 52. Before that is krypton. And so after krypton, I go krypton 5s2, 4d10, 5p, what is it? 5p, 1, 2, 3, 4. 5p4, get rid of my krypton. Here's my outer electron configuration for tellurium. That's about as easy as things get, right, ladies and gentlemen? Sure are. Okay, so moving on. Consider the neutral sulfur, sodium, and vanadium atoms. Hey, I think I recognize those. Determine the number of valence electrons. Okay, so we want to have some notes here on valence electrons. So, what are valence electrons? Well, valence electrons are very important to us. First of all, let's define them. Valence electrons are, let's just do it this way, right? Let's go with our kind of concept map. What are valence electrons? Definition, we'll go on this side for definition. They are electrons. This is usually the case, okay? Usually, now you find some exceptions later, but for us, this is what we're going to say. Electrons in the highest energy level. And when you see the words energy level, what do you always think? In the highest N, right? That's what valence electrons are. Now, why are they important to us? They're important. The importance. Their importance is that they are the electrons involved usually in bonding. It's not your core electrons, it is the valence electrons that are involved in bonding. And then what's the process? And the process is find your outer electron configuration. 2, ID the highest N, and count electrons in highest N. Okay, and this first, the first step is really, you really don't have to do that. You could do it looking at any electron configuration, but it's helpful. And then I'm going to also teach you a periodic table shortcut in a second. Okay, so that's kind of our concept map for valence electrons. Good. So we want to find the valence electrons for sulfur. Let's go back to right here. We said, okay, oops, wrong one. Let's go back to right here. We already did our work on sulfur, right? Here's sulfur. We found the outer electrons for sulfur right here. Now what do? We look at the highest N. Well, I have a 3 and a 3. What's my highest N? Well, they're both 3s, so we're looking at N. We're looking for electrons in N equals 3. How many electrons do I have in N equals 3? I have 2 here and 4 there, so that means I have 6 valence electrons for sulfur. It's that simple. Okay, let's look at the outer electron for sodium. Here's my outer electron for sodium. What's my highest N? Well, I only have 3 out here, so N is equal to 3. That's my highest N is equal to 3. How many electrons do I have in it? I have 1 electron, so that means I have 1 valence electron for sodium. And argon, here's my outer electron configuration. Not argon. That's not right. That is vanadium. Sorry about that. Let's go back and check my question here. Yeah, vanadium. Okay, vanadium. Why did I write argon last time? Vanadium. My outer electron configuration for vanadium is 4s2 3d3. Now, what's my highest N? I have a 4 here and a 3 here. What's my highest N? My highest N is equal to what? 4. Now, how many electrons do I have in that 4th level? I have 2. Do these 3 count? No. They are in the 3rd level, so they are not at the highest energy level. The highest energy level is 4. I only have 2 electrons. That means vanadium has 2 valence electrons. Got it? That's not hard. All right. So let's see what you can do with calcium, zinc, and tellurium. Pause me and bring me back when you have an answer. Okay, here we go. Let's look at calcium. We have the outer electron configuration for calcium. What's the highest N? N is 4. How many electrons are there? I have 2, so calcium has 2 valence electrons. Great. Zinc. What's my highest? Here's my outer configuration right here. What's my highest N? Well, I have a 3 here and I have a 4 here. Which one is bigger? That is bigger. How many valence electrons? I only have 2. What about these 10? Well, they're in the 3rd. They don't count. So I have 2 valence electrons for zinc. And tellurium? Tellurium, well, I have a 5, 4, 5. What is the highest? The 5s, and I have 2 sets of 5s. So how many electrons do I have in the 5s? I have 2 here and 4 there. So that means I have 6 valence electrons for tellurium. Excellent. That's all there is to it. All right, now, I did promise you that I'd show you a shortcut. Here's the shortcut. And once again, we use our wonderful magical tool called the periodic table. You know, it turns out that someone had a lot of brains when they put this thing together because they didn't just arrange it in any order. They arranged it so that things that are called groups, that's the columns, that the things that they could call groups share chemical properties. And the reason they share chemical properties is because they have each group, well, I shouldn't say each, for the most part, each group has same number of valence electrons. Now, when you get to the D and F block, you'll find that that's not quite true, that they vary a little more, but for the main group elements, that's true. And what do we mean by that? How can we figure this out? Well, it's very simple. All group 1, here's group 1, have 1 valence electron. All group 2 have 2 valence electrons. Got it? So that means calcium has 2 valence electrons and barium has 2 valence electrons. Lithium has 1 valence, potassium has 1. So everything in group 1 has 1, everything in group 2 has 2. Let's skip over here to my group 13, my boron, 3 valence electrons, my carbons, my carbon group, 4, so everything down here has 4, 5, 6, 7, and my noble gases have 8 valence electrons. Okay, it's that easy. So group 1 has 1, 2 has 2, 13, 3, 14, 4, 15, 5, 16, 6, 17, 7, and 18, 8. Now, these guys in the middle are a little different, but most of the time, mostly, these guys have 2 valence electrons. Now, why is that? Well, because think about vanadium. Vanadium, the outer electron configuration is 4s2, 3d3. Remember, my D's are always going to be 1 energy level less than my S's, so for the most part, all my D's are going to have 2 valence electrons because my D's are always going to, the electrons are always going to come out of here first, right? Before they come out of my D's. Okay, so that's the hint for your periodic table. Any questions? All right, that's it. And that's it for electron configurations. Next time we talk, we'll be talking about the periodic table and periodicity. All right, hi-ho.